All right, welcome. Today, we're going to piece together this absolutely massive puzzle. And I mean, this is a big one. It involves entire continents, fiery volcanoes, and this incredible slow motion dance that's happening literally right under our feet. We are talking about plate tectonics, the amazing theory that explains the very forces that shape our world. So, have you ever just looked at a world map and wondered, why are all the big geological events, the towering mountain ranges, the powerful earthquakes, the volcanoes, why are they all clustered together in these specific lines? It's definitely not random. It's like they're following a pattern. And that pattern, well, that's our first big clue. It's a huge hint that there's some kind of powerful, hidden force connecting all of it. To really understand that force, we've got to rewind the clock a bit. We need to go back to when scientists first started noticing these little clues right on the surface of our planet. Clues that suggested our world used to look very different than it does today. And the first clue was actually remarkably simple, something you could spot yourself with a map. If you look at the coastlines of, say, South America and Africa, they look like they could just slot together, like giant jigsaw puzzle pieces. For a long, long time, this was just seen as a weird coincidence. But that little observation, that was the seed of a truly revolutionary idea. And that brings us to the hero of our story, a German meteorologist who was about to propose an idea so radical, so completely out there, that it would take the rest of the scientific world decades just to catch up.
So in 1912, this guy, Alfred Wegener, comes out with his theory of continental drift. And he wasn't just suggesting the continents were shifting around a little bit. Oh, no. He argued that they were all once joined together in one single massive supercontinent that he called Pangaea, which means all Earth. I mean, for its time, that was an absolutely extraordinary claim to make.
But here's the thing. Wegener wasn't just guessing. He had evidence to back it up, a lot of it. Beyond the whole matching coastlines thing, he found fossils of the exact same ancient plants and animals on continents that are now separated by thousands of miles of ocean. He pointed to rock formations that were identical on both sides of the Atlantic. He even showed how ancient climate data, like finding evidence of glaciers in modern-day Africa, only made sense if the continents were once joined together in totally different places on the globe. But here was the big problem. What force could possibly be powerful enough to shove entire continents across the face of the planet, right? What was the engine? Without a believable mechanism to explain how it all worked, most of the scientific community just dismissed his ideas. He had all this compelling evidence for what was happening, but he was missing that one crucial piece, the how. And that missing piece, that engine Wegener was looking for, would stay hidden for decades. And ironically enough, the key to understanding how the giant continents moved was found lying deep down on the ocean floor. See, after World War II, we had all this new technology that let scientists map the ocean floor in detail for the first time. And what they found down there were these enormous underwater mountain ranges called mid-ocean ridges. And it was right there, at these ridges, that they found the proof of a process called seafloor spreading. This was the engine Wegener had been searching for. The process basically works like a giant geological conveyor belt. First, hot magma from the mantle rises up at these mid-ocean ridges. Then, as it hits the cold ocean water, it cools and hardens, forming brand new oceanic crust. And then this new crust literally pushes the older crust away from the ridge on both sides. And the continents, they're just getting carried along for the ride. With the discovery of seafloor spreading, that final piece of the puzzle just clicked right into place. Suddenly, Wegener's old continental drift idea was reborn, and it evolved into the comprehensive, powerful theory we know today. And that is the theory of plate tectonics. It says that the Earth's rigid outer shell, the lithosphere, isn't one solid piece. Instead, it's broken up into these massive, interlocking plates, kind of like a cracked eggshell. And these plates are floating and slowly gliding over a hotter, semi-fluid layer of the mantle below, which is called the asthenosphere, driven by forces like seafloor spreading. And all the action, all the drama, the earthquakes, the volcanoes, the mountain building, it all happens at the edges of these plates, at what we call boundaries. At divergent boundaries, plates pull apart from each other, like at those mid-ocean ridges. At convergent boundaries, they collide. They either crumple up to form mountains, or one plate gets forced under the other, creating volcanoes and deep ocean trenches. And finally, at transform boundaries, they just grind past each other, building up all that stress that eventually gets released as an earthquake. And if you want a perfect real-world example of this, look no further than the Ring of Fire. This massive ring around the Pacific Ocean is basically a huge chain of convergent and transform boundaries. It's where a bunch of different plates are all interacting, and it's responsible for about 90% of all the world's earthquakes and most of its active volcanoes. It is plate tectonics in action, plain and simple.
So, why does all this matter? I mean, why is it so important? Because understanding these immense forces isn't just some abstract science lesson. It actually lets us innovate and engineer solutions to live more safely on this dynamic, constantly moving planet of ours.
This knowledge is how engineers can design these incredible life-saving structures. For instance, instead of building on a rigid foundation that would just crack during a quake, they can use flexible base isolators that move with the ground. They can use shock-absorbing materials and design buildings that are meant to sway and dissipate all that energy rather than just collapsing. This is science that literally saves lives. So in the end, the journey from a simple observation about coastlines to a full-blown theory that can help predict geological activity, well, it's just a beautiful example of the scientific process. It took decades of curiosity, of piecing together evidence, and of new technology to finally solve our planet's great moving puzzle. And you know what? That puzzle is still being put together. The plates are still moving right now, as you're listening to this, reshaping our world at about the same speed your fingernails grow. It just reminds us that our planet isn't static. It's alive. It's constantly evolving. And it leaves us with one final, fascinating question to chew on. If this is how much has changed, what will the Earth even look like in the next 200 million years?